Nanoparticles, groupings of atoms just 1/1000th of a meter in diameter, are all around us. In the air we breathe, in specks of dust and debris, wind gusts, even left over from forks. But why are they so special?
Just like how Daenerys is known for her dragons, or Harry Potter for his scar, nanoparticles are considered extraordinary because of their size.
When a material is grinded down to nanoparticle size, whether by nature or in a lab, proportionally less and less of the material makes up the inner pulp of the particles, and more makes up the surfaces. Since more of the material is directly exposed to its surroundings, many of its original properties change, such as chemical reactivity and melting point. More surface area also means a lot more sunlight absorption. Imagine enhancing solar panels with nanoparticles. You would be able to scatter light and capture a lot more solar energy with the same amount of material.
When it comes to nanoparticles, gravity doesn't really matter as much anymore. Stronger subatomic interactions, such as magnetism, tend to take the lead. To really understand this, let's take a look at magnetic nanoparticles.
Magnetic nanoparticles demonstrate a trait called superparamagnetism, which means they align their own magnetization, or poles, with that of any applied magnetic force field. Think of it like a giant game of Simon Says. The moment Simon comes into the picture with his magnetic field, a sudden copycat effect takes place all the way up from a nanoparticle's atom's electrons. Unpaired electrons, or electrons that don't have opposite spinning twin electrons in their clouds of motion that cancel out their own spins, suddenly line up their spin axes the same way as Simon's magnetic field, causing their atoms' net magnetic moment to line up too. When all atoms do this, the magnetic nanoparticle's entire magnetic domain lines up. Now, since Simon's north pole faces the nanoparticle's south, opposites attract and the nanoparticle will move towards Simon.
This low coercivity, or high obedience to magnetic effects, is one of the reasons why nanoparticles have the potential to revolutionize our world. In emerging medical treatments, such as drug delivery, drug-carrying nanoparticles are led to tumor sites by magnetic fields. In magnetic hyperthermia,
an alternating magnetic field is used to make nanoparticles shake in place and create enough heat to destroy cancer cells. Protein-coated nanoparticles are even being used to create some COVID-19 vaccines, acting as antigens and helping the body generate more antibodies.
Nanoparticles are inspiring breakthroughs in tech, such as claytronic atoms, nano-sized computers that apply the physics behind nanoparticles to change their orientations and properties, potentially shape-shifting an entire object to become an entirely different object.
From renewable energy to medicine to innovations in technology, nanoparticles will define our future.